Hello students, this video is to review the multiple choice questions from chapter 4. We're going to be talking about all sorts of different topics, anything from bias to different types of clinical trials like double-blinded ones to use of the random number table. We're going to be talking specifically about those topics and more. At the top of the video here, let me give you the correct answers. Let me give you the answer key here. These are all of the answers to all the questions from 1 through 24. Now, in the next couple of minutes, I'm going to try to go over each one of these questions as quickly and as thoroughly as possible. Well, strap in. Here we go. In question 1, it talks about exampling samples of 2 square meter plots from all of these different areas, some from floodplains, some from coast, some from foothills, and some from high hills. The important part of this is we're doing separate random samples from each of these 4 different strata. As soon as you think of it like strata, you should think of it as stratified random sample. We're not doing voluntary response because the different areas don't choose whether or not to respond. A simple random sample wouldn't have them separated first. A convenience sample would be simply walking out into each of these different areas and finding the most convenient one, and a cluster sample would be going to one of these areas and choosing all of the different plots from only one of those areas. Number 2, your stats teacher has 30 students, and you're supposed to choose a simple random sample. That SRS means simple random sample of 5 students. You have all of these labels from 0, 1 to 30. So what you're going to do by using this table of random digits is go through and choose 2 digits at a time, skipping anything that's above 30, skipping 00, and ignoring repeats. The first one I'm going to choose is 14. The next one I can't use. 45 is not represented here. 92 is not represented here, and 60 is not represented here either. We keep on going to 56, then to 31, which is super close because we're going from 0, 1 to 30, but 31's not there. 42 is not there either, but don't worry because we're getting there. 48 is not there either, but 03 is a winner. So I got 14 and 03 so far. So I'm able to eliminate this one and this one. Now I know 14 and 03 are my first 2. I keep going. 71 is no good. 65 is no good. But 10 is another good one. We have a 10 here, a 10 here, and a 10 here, so we keep going. Next we have 36. Then 22. That's another winner. We got a 22 here, and a 22 here, and a 22 here. This one we can eliminate before looking at the others because we got 2 repeats here. So my next value is 53, which is no good. A 22 is a repeat. A 49 is no good, but 06 is definitely one we're going to use. So that's our choice D. Number 3 is a vocabulary question. When we take a census, we're trying to collect data from every individual in the population. The 2020 census just concluded, unfortunately, and that census was trying to collect data from every individual in the population. That's the definition of census. For number 4, an example of non-sampling error that can reduce the accuracy of a sample survey. Well, let's look through and figure out which one of these is not an error. Choice D is not an error. Variation due to chance at choosing a sample at random. That's fine. That's what we expect in statistics. That's why we consider sample values to be statistics and population value to be parameters. We think there's definitely going to be a difference between the two. We can also identify the ones that are sampling errors. Using voluntary response to choose the sample, that is a sampling error. It's an error in choosing the sample. Using the telephone directory as a sampling frame, not everyone is listed in the directory, so that's another sampling error. These are all errors in the sampling technique. Interviewing people at shopping malls to obtain a sample, that's convenient sample, which is another way of saying a sampling error. The only one that's left is inability to contact many members of the sample. Now, this might seem like a bad thing, and it is in statistics. Sometimes you can't contact members of the sample, but that's not a sampling error. That's an error in the actual procedure of the experiment. A sampling error would be choosing the sample to begin with. This says many members of the sample. The sample has already been chosen here. So this type of error is not going to be sampling error. It is error in implementing the study. Moving on to the next question, question number 5. The simple random sample of 1,200 adult Americans were asked this question. If you read the question carefully, it's a pretty leading question. It's a question that sort of tells you what you're supposed to answer inside of it. It starts with, in light of the huge national deficit, right? Ignoring everything else about the country at large, just saying, in light of the huge national deficit, should we establish a national system of healthcare? And there's only 39% of people that answered yes. That is potentially lower or potentially higher than the actual number. But you would think that in light of the huge national deficit makes people think, okay, if there's a huge national deficit, we should not spend more money, which means fewer people respond yes than is actually the case. So we say that the answer is choice C because it probably undercounts the percent of people who favor a system of national health care. Because without that beginning clause, people might not be influenced to say no. Moving on to question number 6, can changing diet reduce blood pressure? Hopefully. Vegetarian diets and low salt diets, well, they've named these two things here, vegetarian diets and low salt diets. These are two things that could potentially cause a change in the response variable in that high blood pressure. So they've identified these 4 diets. We got normal unrestricted, vegetarian unrestricted, etc. It seems like there's 2 different things that are being looked at, vegetarian diets and low salt diets. And these 4 different diets, these 4 different treatments, are composed of combinations of these 2 things. These 2 things, when used in treatments, are called factors. So a factor would be vegetarian diet, a factor would be low salt diet, and if we're testing both of these factors in all of their different permutations, we're saying there's 2 factors that are being arranged into 4 different individual treatments. So that's 2 factors, normal vegetarian diet normal versus vegetarian diet, and unrestricted versus restricted salt. And question number 7, it says that there's 240 subjects. They're already labeled from 001 to 240, so my sample is already chosen. All of my subjects are already here in my sample. This says that software randomly assigns 60 subjects to each of the 4 diets. This is not sampling, this is assignment of treatments to each of the 4 diets, right? So this is not an SRS. One of the common misconceptions is that this is an SRS because it says random here. Random assignment of treatment, however, is not sampling. Assignment of treatment is something else. In this case, we're talking about a completely randomized design. We haven't blocked any of the respondents based on any of their characteristics. All we've done is taken a totally random list of subjects and randomly assigned 60 subjects to each of the 4 diets. Nothing here indicates blocking. Nothing here indicates matched pairs because we're not flipping a coin and we're not looking at before and afters for the same exact individuals. And this is not observational because we're assigning them diets. Moving on to question number 8. All right, for number 8, one important phrase that you should have identified is 11 pairs of communities. Each pair is going to be similar. We ideally want the pairs to be the same, but each pair is similar in location, size, economic status, and so on. That means that we're identifying pairs that are almost exactly alike. They're as alike as possible. No other confounding variables could potentially creep in and affect our results. So since we have 11 pairs of communities, and in these pairs, there's one community that gets the advertising campaign, and the other one does not. That means that in our matched pairs, we're looking at the difference between one or the other based on the fact that all of them are very similar. This is a classic matched pairs experiment. Yes, I know they didn't say anything about flipping coins in this one. However, they totally telegraphed it to you by saying pairs. Easy. The drug manufacturer Merck recently stopped testing that promising new drug to treat depression. It's a randomized, double-blind trial, which means randomized means we're giving the treatments at random. That double-blind means that the investigators don't know what they're giving and the subjects don't know what they're taking. The dummy pill, another word for dummy pill, is the placebo. That placebo is sort of like a sugar pill, something that doesn't have any drug or anything inside of it. The fact that many people respond to a dummy treatment, so like they take the pill and they believe they're going to get better, that's called the placebo effect. In this next problem, we're looking at corn variety number 1 and corn variety number 2. They're on the same farm, and we know that 140 bushels per acre and 110 bushels per acre are for 1 and 2 respectively. It sort of looks like corn variety number 1 is better than corn variety number 2 because there's more of it than the second one. However, we're not really sure about the effect of this year's drought on them. Maybe corn variety 1 is just better resistant or more resistant to drought than corn variety number 2. So we don't know whether it's strictly superior or whether it's just superior in terms of drought. That seems to me that we don't know which of the possible explanatory variables has made an effect on the response variable. In other words, our initial thought for explanatory variable, which is variety of corn, may have been affected by a different variable, which is this year's drought. This different variable, this variable that could have caused the difference, that's a classic example of confounding, where there's something else in there that might have caused the change that we saw. For number 11, we're looking at the risk of developing Alzheimer's disease. It's asking whether this is good evidence that ibuprofen is effective in preventing Alzheimer's disease. So normally what we need to do in order to determine cause and effect, we're trying to figure out whether ibuprofen causes Alzheimer's to be reduced, right? Or the risk of developing Alzheimer's to be reduced. In order to determine cause and effect, we have to make sure that the treatments are randomly assigned. In this case, we know that the subjects voluntarily regularly took the anti-inflammatory drug ibuprofen, so that means that the subjects weren't randomly assigned to treatments. That means, since there's no random assignment, that we cannot make a judgment based on cause and effect. So initially, we know the answer is no. So we'll cross off all the yeses. Not this one, not this one, and not this one. Now we're only looking at B and D. No, because the effect of ibuprofen is confounded with the placebo effect. Nothing here says that the subjects who voluntarily took ibuprofen were matched on the other side with the other folks that didn't take ibuprofen that took some other kind of pill. It doesn't say that. It just says those who did not. So there's no placebo effect going on here. Since this is an observational study, which is true, we haven't assigned them to do anything. We just observed that some people happened to take this drug and some people didn't. Since it's an observational study, we were not able to, that's right, we were not able to randomly assign these treatments. What we need is to randomly assign treatments to some subjects and some other subjects. That means we need an experiment. That would be choice letter D. Fantastic. Moving on to question 12, double-blind experiment conducted. Remember that double blinding is when the people who are researching don't know what's being given, and the people who are taking the drugs or treatments don't know what's being given. It says that we're trying to keep the diagnosing physicians unaware of the treatment status. That's the definition of double blinding. We're trying to figure out why that's the case. Now remember, this was part of the reading from the textbook. Physicians their job is to save patients, right, as much as possible. So if a physician knows that there's one sick patient and one healthy patient, they're more likely to want to give the sick patient the treatment than the healthy patient, right? That's not because they're bad researchers, that's just because they're good people. So we're trying to prevent physicians from altering the randomization of treatments, which means we're trying to eliminate a possible source of bias. To make sure nobody is harmed, that's not really the reason for blinding. We assume already that the treatment is not going to harm anybody, and we also assume that the non-treatment is going to harm anybody. We're trying to avoid placebo effects, but that wouldn't be altered by the researcher not knowing. We want to make sure that the subjects are randomly assigned to treatments, but double blinding doesn't, like a double blind experiment is already going to have that, regardless of whether it's double blind or not, and this malpractice suits thing is just a throwaway answer. All right, those were the answers and the comments for the first 12 questions in the multiple choice review. I'm going to post another separate video that goes over the rest of the questions in this multiple choice review, so stand by for that. And good luck studying.